last lesson we looked at oxidation states, and I mentioned at the end of the lesson, one of the things we can use oxidation states for is to balance more complex redox reactions. So we can use this because we can look at another definition of oxidation and reduction. So our earlier definition, quick reminder, oxidation meant loss of electrons, and reduction meant gain of electrons. Now, if we have oxidation numbers, we can do a new definition that says oxidation is defined as an increase in the oxidation number. So if it starts with a lower oxidation number, ends up with a higher oxidation number, it's oxidized. On the other hand, if it goes the other direction, we have a high oxidation number and we end with a low oxidation number, it's a decrease, and that's reduction. And as definitions go, I kind of like that one because reduction is a decrease, makes logical sense. So if we look at a redox reaction, the rusting of iron to form iron 3 oxide. Well, if you look at the original substances, we talked about in the last lesson that elements in their natural state, right, where they don't have a charge, have an oxidation state of 0. So the oxygen and the hydrogen and the iron here both have an oxidation state of 0. If we look at our ionic compound here, we know oxygen's -2, but iron, remember, has 2 possible charges. But if we look, there's 2 iron for every 3 oxygen. That tells us that our iron charge is going to be +3. So we can see the oxygen is going from 0 to -2. So that's a drop or a decrease. So we can see that the oxygen is undergoing reduction. Whereas the iron is going from 0 to +3, that's an increase. So the iron is undergoing oxidation. So we're going to look at a bunch of examples and we're going to look at their oxidation states and try and decide whether these things are redox reactions or not. So for each question, again, I strongly encourage you to pause it and try and figure out your oxidation states on your own before you move on. So if we look at our first one, again, we have some elements in their natural state. So those ones, our oxidation state is going to be 0. And we have carbon and fluorine. So if we look back at those rules of last day, there was no rule about carbon and no rule about fluorine. But remember, fluorine is really high electronegativity. It's got the highest. So that fluorine really wants those electrons. So it's going to take the electrons and the charges. And going back to our thing here. So the fluorine's going to be -1, but there's 4 of them. So that says the carbon, to balance that off, it's giving up an electron to each of the fluorines. So it's going to be +4. So we can see that, yep, carbon is going from +4 down to 0, and fluorine is going from -1 up to 0. So which one is reduced there? Well, going down is the carbon. So we talked about the element that is reduced. And which one is oxidized? Well, that's the fluorine. Watch the spelling of fluorine, it's a little tricky. The reducing agent and the oxidizing agent, remember, is the substance that causes oxidation and the substance that causes reduction. So in this case, there's only one reactant. It is both causing the reduction and being reduced. It's also causing the oxidation and being oxidized. So our reducing agent is the substance, right? So the compound that has the thing that's causing the reducing. So in this case, carbon tetrafluoride is both reducing and oxidizing agent. So it's a little tricky. Okay, the next one we have ionic compounds all. So if we have some ionic charges that are easy to figure out, we should do those ones. So we do have some monatomic ions. Sodium is +1. Barium is +2. Chlorine is -1. Barium is +2. Sodium is +1. Chlorine is -1. So there's a few easy ones in this bunch. But then we have the sulfur and the oxygen, and those ones are a little trickier. So the oxygen, we've got our rule that says it's -2. And we have our rule on this side that also says it's -2. And our sulfur is in the sulfate compound. So that sulfate has to balance out to its overall charge. So 1 sulfur plus 4 oxygen have to add up to the charge on the sulfate ion, which is -2. So we don't know sulfur, so we're just going to say S plus 4 times our oxygen has to add up to -2. So sulfur -8 has to equal -2. We bring the 8 over, we get sulfur is 6. And it's in sulfate in both sides, so we've actually done the calculation for both sides. And again, we can double check those. 2 sodiums plus 1 sulfur is going to add up to 8, and 4 oxygens is going to add up to -8, so that is neutral. Likewise, in our substance, the barium sulfate, 1 barium plus 1 sulfur gives us +8, 4 oxygens gives us -8. It adds up to something neutral. So we can see in this question, sodium starts out at 1, ends up at 1. Sulfur starts at 6, ends at 6. Oxygen starts at -2, ends at -2. Barium starts at +2, ends at +2. Chlorine starts at -1, ends at -1. Nothing has changed. So this one, nothing is reduced and nothing is oxidized. This is not a redox reaction. And in fact, any double replacement reaction, which this is not going to be a redox reaction. It's a completely different sort of reaction going on there. So the next one, we have methanol and oxygen forming carbon dioxide and water. Again, start by picking out those ones that you're like, hey, this is one I can do easily. Should be able to do oxygen easily because it's all by itself, and any element all by itself is going to be 0. That's our only element all by itself. But oxygen, when it's not all by itself, we know, is -2. So over on this side, in the carbon dioxide, it's going to be -2, and in the water, it's going to be -2. We also know hydrogen. Hydrogen is usually +1, and it's not an exception here. Gotta make sure things are lining up. When I type things, other stuff is moving. Oh, and I missed the hydrogen here. So that one's +1 as well. So that just leaves the carbon on both sides, which is, well, methanol is a little trickier than the carbon dioxide. Carbon dioxide, we just balance our 2 oxygens with the 1 carbon, so the 2 oxygens makes -4. So the 1 carbon needs to be +4 to make that neutral. The carbon in the methanol, a little trickier. So we have a total here of +3 from these hydrogens, +1 from that hydrogen, so that's +4, -2, so we have a total of +2 that the carbon has to neutralize, so that makes the carbon -2 overall. So with that one, we can see that there are a few things that are changing oxidation states. First of all, that carbon that we just did is -2 on this side and +4 on this side. So that's an increase. So the carbon is being oxidized. The oxygen went from 0 to -2 and to -2. But we did have some oxygen that didn't get reduced. It already started out at -2. So some of the oxygen is reduced, but not all of it. But all we need to identify is what is reduced. So we're just going to say the oxygen is reduced. So this one's a little more typical when we're identifying a reducing agent and an oxidizing agent, because it's going to be two different substances. So a reducing agent is the thing that causes the reduction. So it's the oxygen that got reduced. Well, what caused the oxygen to be reduced? That was the methanol. And the oxidizing agent, remember, is the substance that causes the other substance to be oxidized. So the methanol had the carbon be oxidized. So the oxygen, the thing that was reduced, is the thing that causes that. And I'm actually going to write this one as the symbol for the oxygen, just to remind you that it's that whole substance, right? The oxygen molecule that is the oxidizing agent. Didn't have to do that with the methanol because the name was clear that we mean the molecule. And the last one in this group, we've got, again, some polyatomic ions. Sorry, not polyatomic ions, some ionic compounds. And we have some that are not ionic. So the copper oxide, remember copper has two possible charges. So if we start with the oxygen, it's -2. To make that balance out, when we have two coppers, well, the copper had to be +1. Likewise in our copper sulfide. Sulfide only has one possible charge, and that's -2. The copper has to be +1. So the copper starting out both as +1. Our copper on the other side is by itself, so it's 0. And our sulfur, well, that's got to balance out our oxygen. So we don't have a row about the sulfur, but the oxygen's -2, and it's taking one sulfur to balance out those two oxygens, so it's got to be +4. So when we look at what's reduced and what's oxidized, well, which things changed? Copper went from +1 on this side to 0 on that side. That's a reduction. It's going down. So something must be oxidized. Well, what went up? Well, sulfur started out at -2 and ended up at +4. So the sulfur is oxidized. So if we look at which things cause that, well, the copper got reduced from both things. So the reducing agent, remember, is each of the substances involved. But this one is an aqueous solution. So because it's aqueous, we can remember that sulfide ions are going to be separate. So our reducing agent, we can say, is the sulfide ions. This thing wants me to spell a little bit differently. And our oxidizing agent is our copper 1 ions. So the only reason we can separate this one where we couldn't when we were talking about the methanol or the carbon tetrafluoride and A is these ones are aqueous. So in aqueous solution, we know that those substances are actually separated. So we can use all this to actually balance an equation. And we do it based on the fact that any oxidation numbers that change tells us that we have electrons lost and electrons gained. And we know in an oxidizing reaction, and a redox reaction, that however many electrons get transferred have to be transferred on both sides, right? Electrons gained equals electrons lost. So our steps here, first step is going to be just what we did, identify the oxidation numbers that change. Our second step is we're looking at that increase or decrease of each of those elements and by how much. Third step is we need to multiply to make it so that the number of electrons are going to match. Actually, that's the third and fourth step together. And then we balance anything else that we haven't dealt with. Now, many of these questions you could balance without using this somewhat complicated method. Because if you look at the first question, I'm pretty sure you remember from Chem 20 how to balance an equation like that, right? You've got one carbon on each side, but you've got 4 fluorines on one and 2 on the other. You could balance it just by the method we used in Chem 20. It was called inspection, right? So you could balance it by inspection. And you wouldn't have a problem with that. So this method isn't necessary to balance every kind of equation, but we're starting out with some simpler equations so we can see the method easily before we tackle complex equations like the last two on here. If we look at E, if you try and balance that one by inspection, or F and try and balance that one by inspection, they're both pretty complicated because we have some elements that show up many, many times. So with those elements that show up many, many times, balancing them is going to be a bit more of a challenge. So we're going to look at the method with some easier ones, and then we're going to work our way up to those complicated ones. And I'll probably do a couple easy ones as examples. We'll leave a few to try, and then we'll look at the complicated ones together in class. So if we look at this one, we know what's changed. The carbon is going from +4 to 0. And in case you're wondering where I got these numbers from, it's the same questions we were looking at in example 8. So you can go back to that and look at where the numbers came from. So with that one, we can see that the carbon, I'm just going to write this in here, the carbon is going from +4 to 0, so it's losing 4 electrons. And we're going to do something a little weird here. We're going to say not just 4 electrons, but 4 electrons per carbon atom, or just per atom. And the fluorine is going from -1 to 0. I said that completely backwards. The carbon isn't losing, it's gaining. Reduction is a gain, right? And the fluorine loses, well, it's going from -1 to 0, so that's 1 electron per atom. Now this per atom part, we put it in there because it's going to be really important in some substances. So we have to decide which side of the equation we're looking at because the atoms aren't always equal. The carbon doesn't matter. We've got 1 atom on both sides. So we can say times 1 atom, and we're good. The fluorine, on the other hand, well, on one side we have 4, and on the other side we have 2. When we have that scenario, we usually pick the side with the more, because it's easier to make the side with less to match up to that. So we're going to say times 4 atoms. But we're going to specify in the reactant so that we know what we're talking about. So that, when we do that multiplication, the atoms are canceling out. So we just end up with 4 electrons here. And we also happen to end up with 4 electrons when we multiply the other one. So that means on the reactant side we need to multiply carbon and fluorine both by 1. Well, that works out pretty nicely because they are both on the reactant side together. And then we have to make the product side match that. So to make that match, we put a 2 in front of our fluorine. So, as I said, this was a lot more work than if we had just balanced it by inspection, but we're looking at the method. So next one, let's look at our method again. So this was another one that was one of the examples in 8, so I just got those values in there. And when we look at that, we can see, well, what changes there? It's the carbon is going from 0 to +4. So this time the carbon is losing 4 electrons per atom. And the other thing that was changing was some of the oxygen. So this one's a little tricky. So the oxygen is gaining Well, we're going from 0 to -2, so that's 2 electrons per atom. So we're going to multiply that oxygen by how many atoms we have, but there's oxygen all over the place, so how do we pick where? Well, we know this oxygen in the methanol didn't change. It started out as -2 and ended as -2. So we're not going to deal with that one. We're going to say, let's focus on the one that we know did change. Stuff that started out as 0. So we're going to say times 2 atoms. It's carbons from the methanol, we're just going to say 1 atom. So that carbon works out to 4 electrons. The oxygen works out also to 4 electrons. So we know we don't want to multiply either of those on the reactant side. And let's specify, this is in our O2 on reactants. So we're going to leave the reactant side alone, so that means we know we don't have to mess around with that, we just have to make the product side match, so our carbon already matches. Our hydrogen doesn't quite match, and because that's the only substance we needed to touch, that should automatically make our oxygen match, but we can double check. 1 oxygen plus 2 gives us 3. Darn it, something did not match. Where did I make a mistake? Oh, because my carbon is not 0 here. That's where I made a mistake. So we gotta go back to that. So our carbon is actually, when we look at that, we've got a total of +2. That carbon was -2, not 0. Not sure why we had that was 0. Typo or something. So the carbon was actually going from -2 to 4. That's 6 electrons per atom. Which is going to change this drastically. So take away that 2, that shouldn't be there. So now I have 6 electrons here, 4 electrons here. To make this match up, I can't just leave them be. I'm going to have to multiply to get a common value. Well, a common value for 6 and 4 is going to be 12, right? It's a common multiple. If I multiply the 6 by 2, I'm going to get 12. So I multiply my methanol by 2. If I multiply my 4 by 3, I'm also going to get 12, and we said that was from our oxygen. So we're going to multiply that by 3 to get 12. Now we can balance the rest by inspection. So in this case, our carbon now has to be 2 to get our hydrogen to balance out. Well, we've got a total of 4 times 2, 8 hydrogen over there, so we need 4 times 2, 8 hydrogen over here. Now that double check that I did where we caught my mistake, we're going to do that double check again to make sure I haven't made another mistake. So we have 4 oxygen plus another 4 oxygen is 8, 2 oxygen plus 6 oxygen, 8 oxygen. So do double check that all your elements match up. I didn't make that mistake on purpose, but it did show that checking on that last element is going to help you see if you made a mistake and go back and look for that mistake. So watch out for that. So the next couple, I'm going to suggest that you try C on your own. D and E, as I mentioned, are a little, D, E, and F actually, are a little complex to deal with this method. So we're going to look at these 4 questions in class together, because this is one that I know is going to have some questions, and we'll look at them together so that you can ask those questions.